Hello, and welcome to our program, Astronomy for Everyone. The topic for this month's program is the birth, life, and death of stars. And here to talk to us about it is our guest, Ken Bertin. Ken, welcome back to the program.
Thank you very much. Great to be here.
Good to have you back. It's been a while.
It has.
So we're going to talk about stars.
You bet.
So we start with the Big Bang.
Yep. Do you want me to ask the question first as we go?
Oh, you have a question? Yes.
Yeah. This is just for your audience. Why is the sky blue? Is the question, and we'll get to that a little bit later on, and I will explain that to you.
Great. So we'll have time to think about it.
We'll have plenty of time.
All right. So let's start with the Big Bang.
Okay. Well, we had this event that is figured to be about 13 and a half, maybe 14 billion years ago. That's a long time. The sun has been around here for 5 billion. It's got another 5 billion to go. But when the Big Bang happened, it wasn't a bang per se. It was really an effect of the energy in the universe producing this outburst, if you want to call it that way, but it would not be compared to an explosion. It happened in the first billion years of the universe. You can see the Big Bang is way to the left there, and that was the inflation. It was a very, very fast action. The energy then began to turn into matter, and this is the life, which is, as it says, 13.77 billion years, but it may be longer than that. There's been other things that have been going on that we found out, but that's basically where we are now. There's lots of stars and galaxies. We are now equipped with terminology needed to describe and categorize these stars, and this is what the presentation is about. The history of the universe is that chart, is what you saw. And what you get next is you have the formation of the periodic table. And that, let us take a look at the elements on the periodic table. Hydrogen and helium were here near the beginning of the universe. So from where did the rest of the elements come from?
Good question.
What about the planets and the moons? How do those get there? The answer to all these questions makes sense once we learn more about what goes on inside a star from the moment they are born to the time of their death. The story varies widely based on the makeup of the stars themselves.
When we say that, are we talking mainly size, or are there other things?
There are size and amount of density and the amount of heat, and that is what makes up it. And when we take a look at the Hertzsprung-Russell diagram, you see the different stars. If you take a look at the very, very top ones on the left, those are the O stars. They are very, very hot, some as much as 55,000 degrees at the surface. To compare that, the sun is about 7,000 or 8,000 degrees at the surface. They are very, very, very hot, very dense, and what they are doing, just the same as the rest of them on there. By the way, the phrase that you remember, the type, it's "Oh, be a fine girl" or "Oh, be a fine guy, kiss me." And those are the
various
ones.
letters.
Right. Mm-hmm. And the O are the very, very hottest, and they're also the shortest lived because the life of a star is produced by hydrogen turning into helium. Stars stay together by gravity, but they don't collapse because of the thermonuclear reaction that's going on.
That outward pressure.
That's exactly right. So what you have here is that Hertzsprung-Russell diagram shows you, and if you remember, in about the middle, we are a G star. Our star is the sun, is a G star, has a life expectancy of about 10 billion years. The stars at the very bottom, the red dwarfs and so on and so forth, can live 100 billion years, because they will not use up all the hydrogen into helium. The other stars, like the blue and the O stars and the rest of those up there, they will burn out in a shorter period of time, as I said.
So
Now,
that explains the various life cycles
exactly.
of these stars.
Okay, so they're all a little different. Now, what happens to the star? We know that stars all die because they run out of the hydrogen. And what happens is several things that occur. The thing on the left is the Crab Nebula, and that's a was a very, very, very large star that eventually, as the star died, the hydrogen and helium gravity took over and it collapsed, and then it started burning the heavier elements, expanded again, and then it collapsed, and then it kept collapsing until such time as it exploded. Now our sun doesn't do that. Our sun is going to die out because it will not explode. It isn't massive enough to explode. So this is all entirely dependent on that mass of stars. These pics indicated result of due to the mass of the stars. You've got the exploding star, and then you have a star that's not massive, and that was like our sun. Okay,
that would be the Ring Nebula on the right?
The Ring Nebula, that's M58, 57, I don't remember.
57.
57, right. M57. That stuff is all the stuff that was in the star, all those colors. And in the very middle of that thing is a white dwarf. And the white dwarf could be as much as 200,000 degrees at the surface. It's a very, very hot, dense object, but eventually it will cool and that will happen.
Okay.
That will be the end. All right? So now let's go through the lifetime of a few different types of stars so that we understand the 13 billion years of development in the universe. Obviously, the life cycle of any star from birth to death, and with all the stages in between, spans millions to billions of years, as I said, depending on the star's mass. Stars don't seem to change at all because the human lifetime is a snippet of a fraction of a second, of a blink of an eye, regardless of the mass of the star. So we see a star that we've been here 5 billion, got another 5 billion years to go. Now you can see different images of that star. Those are storms on the star, and there's all kinds of things that are going on right now. We're in a stage which is very, very active, and that's about 11-year cycle. So moving along, again, the path that will follow by a particular star depends mainly on its mass and how much gas was collected and collapsed to form the star. This is because that amount of material will serve as the star's fuel. As we remember from physics and chemistry, when nuclei collide with enough energy so as to become an electromagnetic repulsion between them, the strong nuclear forces take over and they fuse with a small fraction of their mass converting into huge amounts of pure energy. Therefore, only by colliding nuclei together and fusing them in its ultra-hot core can a star release enough outward energy to counter the effects of gravity, relentlessly crushing it inward. This means that the amount of matter that forms the star determines the amount of fuel, and through a variety of other factors, the lifetime and eventual fate of the star. What keeps the star together is gravity, like I said. What keeps the star from collapsing is the thermonuclear reaction, which is hydrogen fusing into helium.
So the two forces are balancing each other
balancing out
to
each
keep
other.
the star in its shape.
Exactly right. All right. Once that action has run its course, gravity takes over and the star starts to collapse. The result is the pressure begins to increase and the helium starts to fuse again, and the word burn works here, obviously, burn. And the star again expands into a red giant. So what we have as a result is the pressure begins to increase and the helium starts to fuse. As the helium fuses, the star collapses again, producing still heavier elements, and the less massive the stars eventually dissipate, producing a planetary nebula with a white dwarf in the center, which cools and dies. The high mass of stars continue to collapse, and upon reaching critical mass, mostly iron, they will explode, and the explosion produces many other of the elements. So
That's
everything,
where the ultra heavy elements, like such as gold and silver.
exactly, that's what we're talking about.
All right.
So that's what you get, all the things, and of course, what we're made of, carbon.
Yep. Exactly.
Carbon. Now, carbon is the type of material, obviously, that will link with other materials and produce something as strong as a life form. Silicon to a lesser degree, but mostly carbon.
Ken, this has
Yes.
been an exciting discussion so far. We're going to take a quick break.
Good.
And if you have a question, please send us an email here to Astronomy for Everyone. And coming up next is Term of the Month with Stephen.
Thanks, Don. The term of the month is hot dogs. An advanced alien civilization might have an easy-to-find unnatural signal. They might build a Dyson sphere. This is a sphere that will use all of the energy of their star. Due to thermodynamics, the outside of the sphere should emit a faint infrared or radio glow. A project searched for candidates using data from Gaia, 2MASS, and WISE surveys. About 5 million stars within 600 parsecs were examined and found 7 candidates. They look like M-type red dwarf stars, but the spectra don't look like stars. And this is what Dyson spheres might look like. Recall that extraordinary claims require extraordinary evidence. Other astronomers have other ideas. 3 of the candidates were quickly found to have nearby radio sources, suggesting that these objects were hot dust-obscured galaxies, or hot dogs. About 1 in 3,000 quasars are thought to be of the hot dog type. We should expect to find hot dogs when looking for Dyson spheres. Further, advanced aliens could make their structures look like natural phenomena for a small fraction of their available power. For example, if they don't want to be easily found. Also, given the 600 parsec radius search, tight limits on the number and lifetimes of Dyson spheres is suggested. Now we have a little bit of an aside here. Our team, Astronomy for Everyone, was given this award by Wyandotte Connects for teamwork. And this is our 15th year of the show.
Thanks, Stephen. We're back here with our guest, Ken Bertin from the Warren Astronomical Society, and we're talking about the birth, life, and death of stars. So, Ken, please continue.
So the last thing that I wanted to mention to you is, in fact, when that very massive star comes to its end, depending on its size, it will either become a neutron star, which is just neutrons, that's it, or a black hole. And everybody wants to know what a black hole is. That's the death of a star. Black holes are black because all they do is bring things in. Nothing gets out.
Nothing ever gets out.
Not even light.
So you would have to have enough mass
Right.
to do that. So a star like our sun has nowhere near
No
the amount of
chance of
mass.
that at all. None.
Okay.
Okay. So what we talk about is, as we said, as the star, the earliest era of star formation, this material is almost exclusively, again, hydrogen helium, as this was what remained after the brief 70 minutes of nuclear synthesis is called, after the Big Bang. That's what it was called. This matter collects due to gravity, pushing increasingly inward as it contracts until things get so hot over a few million years that nuclear fusion begins. That's what lights up the star, establishing an equilibrium and generating a yellow or red main sequence star that glows with all the energy reduced from the collisions happening inside. That's what's going on.
So it's reached that critical mass where the inward pressure ignites.
Exactly. And that's what you've given the mass is the key factor here. Well, so let's start with a low mass star.
Okay.
Low mass star would be our sun. This would range from the smallest the stars can be, meaning the smallest amount of material that can sufficiently trigger nuclear fusion so as to qualify as a star, which is about 13 Jupiter masses. So you get the idea that Jupiter could not be a star, doesn't have enough mass, all right?
Okay.
And the star somewhere in the ballpark of our sun's mass is about right, okay? So that's the first part. So you can see this picture. You got the Earth, look at it. You see Jupiter, nice big object. Brown dwarf, very, very small, but just enough mass to be able to be a star. And then you get these then you get to the larger objects. Obviously,
We have the sun in the upper
is
left corner.
There you go.
So with the low mass star, is there fusion going on there?
There is fusion going on there in a low mass star. All the stars, in order to light up, have to be massive enough to be able to have the change from hydrogen to helium.
Okay, and even with a brown dwarf, there's
Exactly. There's plenty of it there. They're hot enough, and they can do that. Okay?
okay.
All right. Now, they will eventually run out, but it'll be a very, very long period of time. Okay, so as we already know, any star will begin as a cloud of gas and dust and at least a few light years across. Just to give you an example, here's the sun and Sirius. Sirius is the brightest star in our night sky. It is a white star, but it is not a real big white star, okay? It's because it's 8 light years away, so it's very, very bright to us. That's why we see it.
Proximity, it makes up.
Makes up for it. But will Sirius explode? Probably. Okay? Because it has its temperature at its surface is probably in the range of about 20,000 degrees approximately, or 4,000 K. This fusion reaction between the two protons fusing, followed by a subsequent beta delay, and this is a little bit more complex than we really want to get, but I'll just briefly go through it.
Okay.
To get a proton and a neutron, and we call this a deuteron, okay? Deuteron, because, which is the mass of heavy hydrogen, okay? So hydrogen will become deuterium, okay?
Okay.
Then deuteriums are involved in reactions that make helium, all right, which has 2 protons and 2 neutrons. Such a star will continue in this manner for billions of years, slowly fusing all of the hydrogen in the core into helium, as we said, and maintaining a relatively steady size, temperature, and luminosity as it does so, until almost all of the hydrogen is gone. Here things really begin to change. The core of the star will shrink and get hotter, which makes the remaining hydrogen burn even faster. And all of that extra energy being generated will radiate outwards and push the outer layers away from the core. As the outer layers expand, they cool and thus become more and more red. And the star climbs up the red giant branch until we have a red giant star. And actually, that is almost a hypergiant, but we'll get through that in a minute. The star can maintain this new status for a little while longer, around 1 billion years. But after all the hydrogen is gone, the core gets even smaller and even hotter. Moving on to that, at this stage, a phase called the helium flash, things are so hot that the star is able to fuse these heavier elements, heavier helium nuclei into larger nuclei like carbon, as we said, and then oxygen, through something called the triple alpha process. And this means that the star has a whole new source of fuel in all the helium it has been making for billions of years. That's kind of cool, actually.
Yeah.
So the star begins pulsating as it runs through the final energy reserve, entering what we call the horizontal branch. And in this time, it becomes smaller, hotter, and bluer until much of the helium is infused into larger nuclei. So once the core is predominantly carbon and oxygen, with just a shell of helium around it, the shell of the hydrogen around that, and the shell of hydrogen around it, the star has very little material left to burn. So the core will collapse and the star enters an asymptomatic, I can never do that word for the life of me ever, giant branch is what it's called. This means it will grow rapidly and become a giant star again. Remember I said expansion, until
Right.
the last burst of energy to eject the outer layer, pushing it away from the core and back into interstellar medium, leaving only a tiny, very hot, bare core behind around the size of the Earth. This will gradually cool as it has no more fuel to burn, not being hot enough to fuse carbon or hydrogen nuclei, and it will contract further until we are left with a white dwarf star. Very interesting. That is the final star, as you call it, on that. The ejected shell is called the planetary nebula. Do you remember that picture there?
Yep.
Right?
Which has nothing to do with a planet, but
Right, but it's because it's round. It's
There you
probably,
go.
you know how people are, which is misleading since it is not a planet and did not come from a planet. But the name originated from confusion upon its discovery, and it stuck. Okay, so what they saw the planetary nebula. They thought it was a planet initially. The material in a planetary nebula will then become available to join more gas particles to form yet another star. And let me say a side thing on this one. Understanding that our star, is 5 billion years old. The universe is 13.6 or 7 billion years old. What was here before our star? Another star, probably a white star, a little hotter, and before that there was probably another star. In order to that, because again, the white stars, blue stars don't live as long. So you probably had 2 or 3 stars before we got to ours. And what are we made up of? Carbon, silicon, and all the other stuff we have on the planet? That was all built inside a dying big star.
Yep.
Okay?
Right.
That's
So we are star stuff.
we are exactly star stuff, and we are very much star stuff. All right, here's a picture of the comparison of star sizes. The one on the bottom left is our solar system. There it is. Okay, that's our solar system. We have big stars going through there. We have stars like Betelgeuse. If you want to call it Betelgeuse, you can. You're allowed. You have
I
stars
just won't
like
say it 3 times.
yeah, that's right. You got stars like blue-white giant stars and Antares and stars like that. So that's what you're looking at in that. Here is where gravity wins the fight.
Okay.
The star collapses with a single second. The outer layer is bouncing off the core, triggering an explosion, thus ejecting all of the out in space. Goes out in space. This also means one of the most violent energetic phenomenon in the universe is called a supernova. Supernova generates such an unbelievable burst of energy that in a brief moment, dozens of elements heavier than iron can also be synthesized. You get nickel, copper, zinc, silver, gold. Any element with an atomic number greater than 26 is made after the supernova, or a rare event like the collision of 2 neutron stars, or a neutron star and a black hole, where these objects will be discussed in the next segment. That's why these heavy elements are so rare compared to elements like carbon and hydrogen, carbon and oxygen, because stars can't synthesize them the way they can synthesize all the elements up to iron throughout their long lives. And lastly, nature only makes these rare elements during the death of a high-mass star, as I said, or in certain exotic collision events. Supernovae are so bright that they are brighter than the entire galaxy in which they live. When viewed through telescopes, and if in our own galaxy, they even become visible to the naked eye, like the one that generated the famous Crab Nebula, which happened with the civilizations of 1054. A supernova does not leave behind a white dwarf.
Ken, this has been a fascinating discussion. I want to thank you for taking the time out of your schedule to
Appreciate
come
it.
down to the studio and inform our viewers all about it. Please visit our club website. We've got the address down there for you at the bottom of the screen. And coming up to finish up the show is Stephen with What's Up. But before we go to Stephen,
Let's answer the question.
the answer to the question.
Okay, here we go. It'll only take a second. Look at the rainbow. What do you have on the color on the outside? Red.
Oh, red. Okay, I'm looking the other way.
Inside, blue.
Okay.
Those are the shorter waves. Those are the longer waves, the red ones. So what you happen is the sun goes through about 12 miles up is about 90%, 95% of the atmosphere. It scatters the blue light first. Blue skies.
There you go.
Why does the sun look red when it's near the horizon? Because it has 39 times as much distance to go through the atmosphere. So what's left over is the red and orange. And lastly, when you have a lunar eclipse, it's copper red, correct?
Correct.
Right? Because the sun's light goes through all the way through the atmosphere and then lands on the moon, and the only light that's left over is red. There's your answer.
Thank you, Ken.
You bet.
Coming up next is Stephen with What's Up.
Thanks, Don. What's up in the night sky for November 2024? We just had Halloween, which is a cross-quarter day. The lengths of days are slowing in their changes as we approach the coming solstice. Now, November starts with a new moon on the 1st of November. First quarter is on the 9th, full moon on the 15th, and last quarter on the 22nd of November. Then we have, shown here on the 16th of November at sunset, we have Mercury and Venus. Now, Mercury goes from Libra to Ophiuchus over the month, and it has maximum elongation. It is farthest visibly from the sun here on the 16th, and still it is very close to the sun. I think Mercury is going to be, it's an evening object, but it's going to be very hard to spot. Venus goes from Ophiuchus to Sagittarius and sets an hour and a half to 3 hours after sunset, so it's better at the end of the month. And finally we have Mars, Jupiter, Uranus, Neptune, and Saturn, shown here on the 1st at, a few hours after sunset. Mars is in Cancer all month, rises 5 hours after sunset to 4 hours after sunset. It's a little bit better at the beginning of the month. Jupiter is in Taurus and rises a little bit after sunset to just about sunset, as it is approaching opposition on December 7th, when it will be up all night. So Jupiter is up most of the night. Saturn is in Aquarius, and it rises 5 hours before sunrise to 7 hours before sunrise over the course of the month. Uranus is in Taurus and rises, like Jupiter, very close to sunset, and in fact it has opposition on November 16th. Neptune is in Pisces and rises 2 hours after sunset to an hour after sunset. And that is what's up in the night sky for November 2024. Remember, we don't charge money for this show, but we may tax your brain.